In this video, we are going to talk about the concepts of section 3.2, which is titled In Search of an Octet, Ion Formation. So in the previous video, we learned that ionic compounds are going to be formed by two charged species. Positively charged ions are known as cations, and negatively charged ions are known as anions. If we look at the figures in this slide, let's first understand why is it that metal elements actually are willing to lose one or more electrons in order to form cations. Here we have the example of sodium atom. Sodium atom, when we look at the electron configuration for it, of the 11 electrons that it has, we know that its electron configuration is 1s2, 2s2, 2p6, 3s1. So overall, in this electron configuration, we can see that in its outermost shell, it has one electron. Now, that one electron, which is a valence electron, is going to be lost. And when sodium loses one electron, then because it lost a negative electron, it's going to now have a positive sign. So it goes from sodium atom, which you can see here, the Lewis structure for it. And then that is going to turn into sodium ion, where it's forming a cation. When that occurs, that means that now sodium has specifically 10 electrons. And those 10 electrons are going to have the electron configuration 1s2, 2s2, 2p6 overall. Now, we learned previously that at times there's are electron configurations that can refer to some elements in the periodic table that are very stable, and they actually are virtually unreactive. So what we see overall is that upon sodium losing an electron, now the 10 electrons that are populating that sodium ion that forms are going to be very similar electronically to a particular noble gas. And this one overall is going to be like neon. So metals elements, when they lose their valence electrons, what they're going to do is that they're going to gain stability, similar to the stability that noble gases have. So we can observe that in the case of sodium, that valence electron that is in the 3s1 shell and subshell is going to be lost in order for now sodium ion to have a similar electron configuration to the noble gas neon in this case. So metals overall will lose valence electrons, and as a result, they are going to be electronically similar to noble gases in the periodic table. Now let's look at an example of why is it that nonmetals, on the other hand, are going to be accepting electrons to reach very similar electron stability overall. So let's explore actually what happens to the chlorine atom. So what we see overall here in the left side of the arrow, we have chlorine atom. We can observe that this is the Lewis dot for the chlorine atom. A chlorine atom has 17 electrons. Those 17 electrons live specifically in 1s2, 2s2, 2p6, 3s2, 3p5. So overall, chlorine is going to be willing to gain a valence electron. So when chlorine accepts that valence electron, we observe that now instead of having 7 dots in its outermost shell or valence electrons, is going to have 8. Electronically, now that chlorine accepted that electron, its name is going to change into the chloride ion. So the correct way to write the name for nonmetals when they have accepted electrons is that it's going to end in ide or IDE. So that's why it goes from chlorine to chloride. Now the chloride ion has 18 electrons overall. Those 18 electrons are going to have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now, electronically, chloride ion is able to do this. And now when we look at the periodic table, to which element in the periodic table that is unreactive and it has a stability shares that electron configuration, this is going to be argon. So when chlorine accepts an electron, electronically, those electrons are going to be similar to the electrons that argon possesses. And we already seen the stability of noble gases. So let's understand overall that nonmetals are going to be gaining valence electrons, actually producing anions that electronically are going to be very similar to noble gases. Now, one more thing that I should say when it comes to this is not that the elements want to be specifically neon or argon. It could be any of the noble gases that are present in the periodic table, that those atoms are going to give away electrons in the case of metals or gain electrons in the case of the nonmetals in order to form these charged species. When it comes to how do I know which noble gas is going to be present once my metal loses electrons or my non-metal gains electrons, we can observe that in the following table, it has summarized how the metals that lose valence electrons, there is an atom pointing at the noble gas that they will form once they lose their valence electron. So you can see that lithium, once it loses one valence electron, is going to look like helium. Sodium, magnesium, aluminum is going to look like neon. Potassium, calcium ion will look like argon, so on and so forth. We can see on the yellow side, on the right side of that figure, that it also has the information for when nonmetals gain valence electrons. So we can observe overall that the nitride ion will look like neon. The oxide ion will look like neon. The fluoride ion will look like neon, so on and so forth. So we can see overall that the elements are going to either gain or lose electrons in order to obtain these noble gas electron arrangements. So overall, when it comes to the octet rule, as you remember from a previous video, most noble gases, except helium, are going to have 8 electrons in their outermost shell. So the octet rule refers to those 8 electrons that most noble gas arrangements have in their outermost shell. Now, in addition to the group number, giving us information about the valence electrons, it also can give us information about the ionic charges that a particular element has. And as you can observe here, when it comes to group 1A, all of the elements in that column, and here we don't have hydrogen illustrated because hydrogen is going to be a special element that can form cations, and at times it can form anions. But overall, in group 1A, we can see that lithium, sodium, potassium, rubidium, cesium is going to have a +1 charge. All of them. In group 2A, we have magnesium, calcium, strontium, and barium. Their group number is 2A, so that's why we observe that all of them make that +2 charge. In group 3A, aluminum, and let me just include 2 more that are not illustrated here, gallium, and indium are also elements that are going to have a +3 charge or 3+ charge because of where they are in the periodic table. As you can visualize here, and I'm just going to write it as a note, group 4A can form cations or anions. So that's why it's not included in this table. So they have a different situation in there because of the variety of elements that are there. The trend continues with the non-metals that are in 5A, 6A, and 7A. So in 5A, you guys are only responsible for knowing how nitrogen can gain 3 electrons, how phosphorus can gain 3 electrons. From group 6A, you can see how oxygen can gain 2 electrons, sulfur can gain 2 electrons, selenium, which is not illustrated here, can also gain 2 electrons. And lastly, when it comes to the halogens in 7A, each of them can only gain 1 electron in order to obtain their noble gas. So that's why the charges overall for them in 5A is -3, in 6A is -2, in 7A is -1. Now, in the periodic table, we actually have a special set of elements that have variable charges. And these elements that have variable charges are known as transition metals. The transition metals are present in group B in that section in the middle of the periodic table. In this table, which is obtained from a different textbook resource, is giving you a little bit of an overview of the different elements that have variable charge. But we are going to learn later in the videos how to derive the charge for elements that have variable charge. Now, in chemistry, we have exceptions to the rules. And when it comes to the transition elements, there are 3 elements that only form one type of cation, because these elements with variable charge refers to transition metals. And as we learn, transition metals make cations. So when it comes to the 3 elements that are in the area of transition metals, but they don't have multiple charges, it includes zinc, and zinc always forms a +2 charge. Cadmium, which always forms a +2 charge, and silver. Silver always form a +1 charge. Only those 3 have only one type of cation. In addition to the transition metals, there's going to be 4 additional elements that, even though they don't live in the area of the transition metals, they have variable charges. And that includes tin, antimony, lead, and bismuth. Even though they don't live specifically where the transition metals are, they also form variable charges. So far, we have seen how there are metal elements forming cations, how certain non-metal elements form anions, And now let's introduce one more group that are part of this formation of ions overall in ionic compounds. That last group is going to be polyatomic ions. Polyatomic ions are a group of atoms that have an overall charge that consists of nonmetals that are phosphorus, sulfur, carbon, nitrogen, and oxygen, that when they are combined together, they're going to form this polyatomic ion. Poly means multiple, atomic refers to atoms, and ions, we will see that they form charged species. You guys are going to be responsible for knowing all of the polyatomic ions that you see in the following slide. So let me just write here a note. Please memorize the list of polyatomic ions that you see in the following table. Out of all of these ions, understand that there's only one polyatomic ion that it is positively charged. You see it highlighted with that red dotted line, and that ion is called ammonium. Its chemical formula is NH4+. So that is a cation out of the polyatomic ions. The rest of the polyatomic ions are negatively charged. They have different charges. Some polyatomics are -1, some polyatomic ions are -2, some polyatomic ions are -3. My recommendation is that you make a list of all the negative charge ions depending on the value. So all the -1s, all the -2, all the -3, and you memorize their chemical formula and their name, because in the next video, we're going to learn how to utilize that information of cations and anions to actually not only write chemical formulas, but to name particular ionic compounds.